Okay. Hello everyone. Good evening. I think I'm audible, right? Okay. So this is lecture number 4 of calculus. So we are seeing continuity and differentiability. So this is lecture number 4 of calculus. From the previous class, we have started continuity and differentiability, and also we have introduced the definition of continuity and differentiability. And I think we have solved three problems, right? So I'll just show you the notes of the previous class. Previous class, we have defined what is meant by first we have defined continuity at a point. Then we have defined what is meant by continuous function. So just recall the definition of continuity at a point. At a point A, f is continuous. At a point A, f is continuous if a limiting value is equal to function value. So limit extending to a f of x equal to f of a. So limiting value has to be equal to function value at that point. If that happens, we say at that point it is continuous. If it is true for each of its point in the domain, then we say it is a continuous function, right? And the differentiability we have defined. So L of f dash of a, R of f dash of a, both has to be equal to be differentiable function, to be differentiable at that point A. And then we also gave examples that differentiability at a point implies continuity at a point, but continuity at a point does not imply differentiability at a point, right? That also we have defined. After that, we have solved first problem, this problem number 2, this problem number 3, right? So we have solved three problems as of now. So we're going to this video also is completely based on continuity and differentiability only. So we're going to do many problems. Um, we have solved three problems, right? So we'll start with the fourth problem. After that, we will discuss more about continuity and differentiability. So we'll start with fourth problem, right? So for the past 1 week, I didn't work, so I couldn't receive my classes. From now on, we will have a regular class. Okay. So we'll start session number 4. So in the previous class, we have solved three problems. So we'll start with the fourth problem. So problem 4. So discuss the continuity of the function g(x), right? So 4. So discuss the continuity. As of now, all three problems are based on continuous functions only. So this also based on continuity only. After some time only, we'll start solving problems based on differentiability. To discuss the continuity of the function f of x is equal to g(x), right? So g(x). So what does g(x) means? So g(x) means greatest integer less than or equal to x. Greatest integer less than or equal to x. So greatest integer less than or equal to x. This is called g(x). These are very simple definition that you come across in schools, right? So what is g of 1.5? So you need to find a number that is less than 1.5, and also it has to be greatest, and also it has to be an integer. So it is 1, right? See, very simple. Just plot 1.5. You just find the left hand side first integer. So what is left hand side first integer? It is 1, right? So gif of 1.5 is 1. So it has to be left of that. It has to be greatest. So you just see which number is to the left of that left to first number. That's it, right? What is gif of 1.9? Again, it is 1. So 1 point greatest integer is less than 1.9. So it is 1, right? What is gif of 0.9999? It is 0, right? So 0.999. So what is the greatest number that is less than 0.999? Also it has to be greatest. It is 0, right? And what is diff of minus 1.5? So it is minus 2, right? So minus 1.5 is here. So left hand side first number, which is minus 2. And also what is diff of 2? Diff of 2 is 2, because it can be equal to that also. Greatest integer less than or equal to x, less than or equal to x. So diff of 2 is diff of any integer. Diff of any integer is always that integer again, right? Diff of any integer is again that integer only. So these are the basic definitions about GIF-X, right? So very simple definition. So GIF of you need to find a GIF of what is GIF of 10.1. So GIF of 10.1 is 10, right? What is GIF of 10.7? It is 10 again. What is GIF of 11.5? It is 11. So 11.5 left number, first integer. That's it. What is diff of minus 10.5? It is minus 11. So minus 10.5 left hand side first integer. If it is integer, it is integer only. So diff of 2, 2, diff of 3, 3, diff of 4, 4, diff of 0, 0. Okay. So first what I'll do is we will define gif-x. So I'm going to define gif-x to be 0 when your x belongs to, when your x lies between 0 and 1. Yes or no? When your x lies between 0 and 1, your gif-x is 0, right? Because what is gif of 0.9? It is 0. Gif of 0 is 0. Gif of 0.8. So any number in this interval, gif is always 0. And it is 1 when your x lies between 1 to 2, right? See, I'm using open interval here. So 2 is not included here because gif of 2 is 2. If your x lies between closed interval 1 and open interval 2, your gif-x is 1. And it is 2 when your x lies between 2 to 3, and it is minus 1 if your x lies between minus 1 to 0, right? Your x lies between minus 1 to 0. Whenever x belongs to interval, left hand side first integer. If it is decimal, if it is minus 1 means this is minus 1. Greatest integer less than or equal to x. And it is minus 2 when your x lies between minus 1 and minus 2 to minus 1. It will go on and on. And it is 3 when your x lies between 3 to 4. It will go on and on, right? So this is the definition of, this is the definition of gif-x. Now we'll try to draw the graph for this gif-x. We'll try to draw the graph for gif-x. So here it is 0, 1, 2, 3, 4. It is minus 1, minus 2, minus 3, and so on. Now you can see when x is 0, it is 0. 0 to 1, all the values are 0. But at 1, I'm just putting a hole here because at 1 it is not 0, right? So when your x belongs to 0 to 1, including 0, all the outputs are 0. This is 1, 2, 3. When your x is 1, it is equal to 1. And if your x belongs to 1 to 2, all the input outputs are 1. But at 2 is not defined, right? I'm just putting a hole here exactly at the top of 2. When your x is in 1 to 2, your output is 1. At 2, output is equal to 2, equal to 2, and then all are equal to 2 when your x belongs to 2 to 3, and then I'm putting a hole here because at 3 it is not 2, right? It is not 2, it is 3. And then from 3 to 4 all are equal to 3 except 4, so I'm putting a hole at 4. And similarly, when x is minus 1, the output is minus 1, and in between 0 to minus 1, output is also minus 1. But at 0, I'm putting a hole here because at 0, the output is not minus 1. And then um, from minus 1 to minus 2, again I'm putting a hole here. At minus 2, it is equal to 2. Then all are equal to 2. And this number is minus 2, right? This will go on and on, right? This will go on and on. So at -2 it is open, and at -3 it is -3, and this number is -3. So this is the graph of GIF-X, and you can see this function is called a step function, right? It looks like a step, right? So it is called a step function. This is called a step function, and you can see whenever your x is an integer, whenever your x is an integer, when x is an integer, what happens? When x is an integer, or let us say when a is an integer, right? When a is an integer, what happens, right? You can see at 2, what is your LHL actually? Let us take 2. At 2, what is your LHL? Very simple, right? You just go by the graph. At 2, if I approach 2 from the left, where your function is approaching, the function is approaching 1, right? But when I approach 2 from the right, you can see the function is approaching 2. Yes or no? So I can see when I approach 2 from the left, the function is approaching 1. If I approach 2 from the right, the function is approaching 2. So whatever integer point you take, right? Whatever integer you take, I'm just taking 2 for example. At 2, you can see your LHL is 1 and your RHL is 3. And similarly, if I take 4, what is your LHL? LHL is 3. RHL will go to 4. And similarly, when you take 0, so right hand side will tend to 0, but your left hand side will tend to -1. So when A is an integer, LHL is not equal to RHL. That means limit x tending to A, if of x does not exist. Does not exist if A is an integer. Yes or no? If A is an integer, limit will not exist because LHL RHL both are different at A. Whatever integer you take, limit extending to a GIF x does not exist. Any integer you take -1. What is your RHL? It is RHL is -1. What is your LHL? It is going to -2. So when A is an integer, limit extending to a GIF x does not exist. Suppose if A is not an integer, limit will exist, right? For example, you take A to be some 1.5. Let's take A to be some 1.5. So if you take any decimal value, this is your output value, and you can see LHL, RHL, F of that value, all are equal. So what we can conclude is limit extending to a f of x. So that is limit extending to a GIF x does not exist if a is an integer, and this limit will exist if a is not an integer. If a is not an integer, so that means we can conclude that if x is not continuous, if x is not continuous at x is equal to a, where a is an integer, because limit itself does not exist at that point. How it can be continuous? Limit exists and has to be equal to f of a, then only it is continuous. Where a is an integer, so whenever a is an integer, limit does not exist, and that implies it is not continuous also. If x is continuous at x is equal to a, if a is not an integer, right? If a is not an integer, and I can see that at a it is not continuous, right? So here I can draw without lifting the hand. I have to jump, and then I have to go here. I have to jump, I have to go here. I have to jump, I have to go here. Now you can see where I am jumping. I am jumping at all integer points. So all integer points are points of discontinuity. All integer points are points of discontinuity, right? All integer points are points of discontinuity. Whatever integer you take, it is not continuous at that point, right? Okay, so as of now, we have solved four problems based on continuity, right? I think you have got some idea how to say a function is continuous at that point. At that point, you find LHL, you find RHL, you find f of a. That is at a, if you want to say a function is continuous at a you find LHL, at a you find RHL, at a you find f of a. All three are equal, we say f is continuous at that point, right? Okay. So we have solved four problems as of now. The last class we have solved three problems. In this class we have started first problem. Now what I'm going to do is I'm going to discuss about the types of discontinuity. I'm going to discuss about the types of discontinuity. I want to do many problems, but I want to discuss this and then I have to do many problems. So types of discontinuity. So types of discontinuity. So first discontinuity is called removable discontinuity. So first discontinuity is called removable discontinuity, right? See, remember the definition, recall the definition of continuity, right? Recall f is continuous, f is continuous at x is equal to a if limit extending to a f of x is equal to f of a. For this limit to be exist, we need to find LHL, we need to find RHL, and both has to be equal. What is the formula for LHL? Limit extending to 0 f of limit extending to 0 f of a minus h. Limit extending to 0 f of a minus h. What is the formula for RHL? Limit extending to 0 f of a plus h. These two has to be equal and has to be equal to f of a. If all three are equal, we say f is continuous at that a. Suppose if it is not equal, we say it is discontinuous at that point, right? Okay. Now, first is removable discontinuity. When a function is said to be removable discontinuity, see, at a point A, it is not continuous. That means not equal, right? If this is not equal, we say it is not continuous. That means we say it is discontinuous at that point. Now, I'm going to classify the types of discontinuity. I'm going to classify the types of discontinuity. So, first discontinuity is called, I'll read it this. So, types of discontinuity. The first one is called removable discontinuity. The first one is called removable discontinuity. When we say at a point A, it is discontinuous. But when I'm going to say at a point A, it has removable discontinuity means very simple. Limiting value exists, function value exists, but they are not equal. Then we say at A, it is discontinuous, but I'm going to call that type of discontinuity to be removable discontinuity. Limiting value also exists. Limiting value exists means LHL, RHL both exist and equal, but it is not equal to the function value at A. If this happens, we say that discontinuous removable discontinuity, right? If if limit extending to A f of x exists, f of A exists, but it is not equal to, but it is not, but it is not equal to f of A. Then we say this, then we say then f is said to have removable discontinuity, removable discontinuity at x is equal to a. So at a it is not it is discontinuous only. How it fails the continuity? Limiting value exists, function value exists, but it's not equal. But that discontinuity is called removable discontinuity, right? Why it is removable discontinuity? Because these types of discontinuity can be made continuous if I can rephrase the function. If I can redefine the function, this type of discontinuity can be avoided if I redefine the function. right? Okay, I'll give examples. I'll give examples. First, I'll write it down all. Okay, what I'll do is, can you have examples immediately after something? I'll give examples immediately after this, right? Example. You consider the function f of x equal to x square minus 4 by x minus 2 when x is not equal to 2, and they are defining this to be 4 when x is equal to 2. Let us check the continuity at 2, right? Let us check, let us see whenever where the function is breaking, that is the point, important point. From that alone, it is enough to check the continuity. All other points, it will be continuous only. Let us check the continuity. Let us check the continuity at x is equal to 2. First, what we'll do is we will find limit extending to 2 f of x, right? See, here I don't need to find LHL, RHL because left hand side, right hand side both are same function only. Exactly at 2 we are defining as 4 not equal to 2. That means right of 2, left of 2 both are this function only. So I don't need to find LHL and RHL separately. Is it clear? The last problem, the last video we have seen left hand side of 2 is another function, right hand side of 2 is another function. There are left of 2, right of 2, both are different definitions. But here not equal to 2. That means left, right both are same function only. So it is enough to find directly limit x tending to 2 f of x square minus 4 by x minus 2. So I'm just doing factorization, or I can apply L'Hopital also. So it is 2x by 1. So it is 2x by 1. So when I put x is equal to 4, it is 4, right? When I put x is equal to 2, it is 4. Actually, it is continuous, right? Okay, let us redefine this function to be 3, just for understanding, right? Let us redefine this function to be 3. Okay. Now we see that limiting value is equal to 4. Now, what is the function value at 2? They have given the function value at 2 is equal to 3, right? I'm just redefining, right? Let us assume the question is like this. Now you see that limit exists, but it is not equal to the function value. Yes or no? It is not equal to the function value. We see that limit extending to a f of x existed, but it is not equal to the function value because this is 4, this is equal to 3. This can be this can be removed if I change this 3 to be equal to 4. Yes or no? If I change this number 3 to be 4, this can be removed, right? So if I redefine f of x to be x square minus 4 by x minus 2 when x is not equal to 2, it is 4 when x is equal to 2. Now it becomes continuous. So at 2 they are given 3. Now if I redefine this function to be 4, it can be made continuous. That is why it is called removable discontinuity. So this type of discontinuity can be removed if I redefine the function based on my requirement. That is called removable discontinuity. What is the number I have replaced here? I have replaced the limiting value of this function to be here, right? I have replaced the limiting value of this function to be here. If I redo like this, then this type of discontinuity can be removed if I redefine the function, right? Now, second type of discontinuity is called, so what is removable discontinuity? Limit existed, function values also existed, but they are not equal. That is called removable discontinuity. Second one is called discontinuity of first kind. Discontinuity of first kind. Discontinuity of first kind. So when we say discontinuity of first kind is, see, This both the limit exist. It is finite only, but they are not equal. In this removable discontinuity, limit exists. That means both are finite and equal, but it is not equal to f of a. But in discontinuity of first kind, limit x LHL and RHL both exist, both exist, but they are unequal. But they are unequal. Then F is said to have a discontinuity of first kind, right? We say it is a discontinuity of first kind. That is, LHL, RHL both exist, but they are unequal, right? It is discontinuous only because limit itself does not exist. Here, limit existed, but it is not equal to function value. It is discontinuous only, but that type of discontinuity is called removable discontinuity. Here, limit itself does not exist, but both the limits value are finite. LHL, RHL exist, but they are not equal. That means limit does not exist, right? I'll give you an example. I'll give you an example. Don't worry. Okay. Let us consider. Let us consider the function. Let us consider the function f of x e power 1 by x minus 1 divided by e power 1 by x plus 1 if x is not equal to 0, 0 at x is equal to 0. Let us check the continuity at 0. Let us check the continuity at x is equal to 0. So first what we'll do is we will find LHL, we will find RHL, right? We will find LHL, we will find RHL. So LHL. So what is LHL? Limit s tending to 0 f of a minus h. So limit s tending to 0. See, I have checked that I have said that in the previous problem, LHL, RHL both are same function. So I have evaluated only this limit, right? So for safer zone, you just find LHL, you find RHL for anything, right? See, I'm just doing this as 4. You just find LHL, RHL at 2, both will be equal to 4, right? Okay. So limit s tending to 0 f of a minus h. So f of 0 minus h. So limit s tending to 0 f of minus h. So limit s tending to 0 f of minus h is e power minus 1 by h minus 1 divided by e power minus 1 by h plus 1, right? Now you can see that this will tend to 1 by this will tend to 1 by 0. When h is 0, this is 1 by 0. So this will tend to e power minus infinity minus 1 by e power minus infinity plus 1. E power minus infinity is 0. This will tend to minus 1, right? This will tend to minus 1. E power minus infinity is 0, right? So what is the graph of e power x? So it will go like this. So when x is tending to minus infinity, where output will tend to 0, right? Now we will find RHL. So RHL is limit s tending to 0 f of a plus h. So limit s tending to 0 f of 0 plus h. So limit s tending to 0 f of h. So limit s tending to 0 e power 1 by h minus 1 divided by e power 1 by h plus 1. E power 1 by h minus 1 by e power 1 by h plus 1. Now you can see that when x is tending to 0, this is infinity minus 1 by infinity plus 1, right? Because e power infinity is infinity only. But at infinity, it will tend to infinity. It will output is as large as you can, as large as you can. So when I see what I'm going to do is, um, this will tend to infinity minus 1 by infinity plus 1, right? So what I can do is, I'm just going to rearrange this, or I'm going to redefine. Let us take e power 1 by h common. So we'll have 1 divided by 1 minus e power 1 by h whole divided by, let us take e power minus 1 by h, 1 by h common here. So 1 plus e power 1 by h. Now these two will get cancelled. Now you can see when x is tending to infinity, this will tend to infinity. So 1 by infinity will tend to 0. This will tend to 1 overall, right? When x is tending to 0, this term will tend to 0, and again this term will tend to 0. So 1 minus 0 by 1 plus 0, overall this term will tend to 1, because this is 1 by infinity, 1 by infinity. We see that we see that LHL is not equal to RHL, but both exist and finite. Both exist and finite, but they are not equal. So that means at x is equal to 0, it has discontinuity of first kind. See, it is discontinuous only because limit itself does not exist. Limiting value has to be equal to function value. Here, limit itself does not exist because LHL and RHL are not equal. The limit does not exist means it is not continuous also. So as x at x is equal to 0, it has discontinuity of first kind, right? So we'll move on to third one, discontinuity of second kind. Discontinuity of second kind. Discontinuity of second kind. So in see, it is not continuous. Just classifying the continuity. First one is limit exists, function value exists, but both are not equal. So at A, it is removable discontinuity. Limit itself does not exist, but both the LS and RSL are finite and not equal. So it is discontinuity of first kind. Now discontinuity of second kind, right? Discontinuity of second kind. LHL limit LHL RHL does not exist, right? LHL if neither LHL nor RHL exist, then we say F as a discontinuity of second kind, right? That is LHL RHL does not exist. That means we say it has a discontinuity of second kind, right? I'll give examples. I'll give examples. Okay, consider the function. Consider the function f of x. Let us consider the function f of x e power 1 by x. Okay, so what I'll do is I'll slightly redefine this. So discontinuity of second kind, right? What I'll do is if instead of neither, just a minute. Okay, what I'll do is I'll slightly redefine this, right? Slightly redefine this. Same only, but I'll redefine this. F is F is said to have F is said to have discontinuity of second kind from the left of A, from the left of A, from the left at A, from the left at A. I'm just going to do as discount of second point from left, discount of second point from right. From left at x is equal to A, if LHL does not exist, right? LHL does not exist. RHL exists. RHL exists. F is said to have F is said to have discontinuity of second kind from the right at x is equal to A if RHL does not exist but LHL exists. LHL exists, right? I'll give examples. To consider the function f of x equal to e power 1 by x when x is not equal to 0, 0 when x is equal to 0, right? 0 when x is equal to 0. Okay, now we can see at 0, what is your LHL? Limit s tending to 0, f of a minus h. So limit s tending to 0, f of 0 minus h. So limit s tending to 0, f of minus h. This will tend to 0. So our LHL is 0, right? Now you find RHL. So limit s tending to 0, f of a plus h. Limit s tending to 0, f of 0 plus h. So limit s tending to 0, f of h. So limit s tending to 0, f of e power 1 by h. This will tend to e power infinity. This will tend to infinity. So this does not exist. That means at x is equal to 0, it has the LHL is 0. That means uh, RHL does not exist, right? RHL does not exist. That means f at x is equal to 0, it has discontinuity of second kind from right, right? So that is see, very simple. Here both the limit exists, both the limit finite exists, but they are not equal. But here one of them is does not exist, other is exist, right? So we're going to call this discontinuity of second kind, right? Discontinuity of second kind. Okay, okay, okay. So next is mixed discontinuity. Last type of discontinuity, that is called mixed discontinuity. F F as a mixed discontinuity. F as a mixed discontinuity at A if either this happens, right? I'm going to give two conditions. First is LHL does not exist, right? LHL does not exist. RHL exists. This is same as saying this is going to be of first kind. However, RHL exists, right? RHL may or may not equal to f of A. May or may not equal to f of A, right? However, RHL may or may not be equal to f of A. See, it is same, right? There is not much difference between discontinuity of second kind and mixed discontinuity, right? LHL does not exist, RHL exists, but this number exists, right? This number need not be equal to f of a, right? Then we say it is mixed discontinuity at a, or RHL does not exist. Sorry, RHL does not exist. LHL exists. However, LHL may or may not equal to f of a, right? This is very simple only. So we say this function as a mixed discontinuity. Right? It is not that much important. Actually, this topic is not that much important, but I'm just telling you there are four kinds of discontinuity. Right? Okay. So as of now, we have solved four problems based on continuity, and then we have discussed the types of discontinuity. Right? Now we'll do more problems. Problem number 4, 5 will start. Right? Problem number 5. Problem number 5. Okay. Discuss the continuity of the function f of x is equal to sine 1 by x at x is equal to 0. Very, very important idea. What I'm going to do is at x is equal to 0, we need to define, we're going to analyze the continuity at 0 for this function sine 1 by x. Right? First, what we'll do is we'll find limit x tending to 0 f of x. So limit x tending to 0 sine 1 by x. Very, very important idea I'm going to tell now. Always remember sine 1 by x when x is tending to 0, limit does not exist. Limit does not exist. It oscillates, it oscillates, it oscillates between the open interval minus 1 and 1. See, this is called, it oscillates between minus 1 and 1. What happens is when x is tending to 0, it oscillates between minus 1 and 1. So we call this as a butterfly graph. How the butterfly will flutter. So at 0, when x is tending to 0, it will flutter between minus 1 and 1 because sin x maximum value is 1 and sin x minimum value is minus 1. So when x is 0, this will oscillate between minus 1 and 1. It will flutter like anything. I will show the graph of sin 1 by x. So always remember at x is equal to 0, sin 1 by x graph oscillates between minus 1 and 1. Right? Oscillates between minus 1 and 1. You can see that and sin 1 by x. I have drawn the graph of sin 1 by x. You can see what happens at 0. You can see that it looks like a thick band, right? But actually it oscillates between minus 1 and 1. When I get closer and closer and closer and closer and closer, you can see that you will get an infinite number of chips here. You'll always get as chips, right? It may look like a thick, it may look thick, right? But it's not thick. Actually, there are infinite lines here. That means it oscillates between minus 1 1. You can't even imagine how it is. You can see when I zoom it here, you can see how big gap is, right? So at x is equal to 0, the function will oscillate like anything. It will flutter how the butterfly will do. That's how will happen for this function sine 1 by x, right? Sine 1 by x at x is equal to 0, it oscillates between minus 1 and 1. You can see this is minus 1 and this is plus 1. When at 0, flutter like anything. It will flutter like anything, right? So always remember for sine 1 by x, at 0, the limit does not exist because your LHL and RHL both will flutter between minus 1 and 1. So you can see that limit x tending to 0 sine 1 by x does not exist because see limit itself does not exist, right? That means it is not continuous also, right? It is not it is not continuous at x is equal to 0. Now what about this problem 6, right? Discuss the continuity of the function f of x is equal to x into sine 1 by x when x is not equal to 0, 0 when x is equal to 0. What happens to this function, right? Here I multiplied with x and then we have and then I have defined at 0, I'm going to define this as 0. Let us see what happens at 0, right? Suppose what we'll do is we'll find LHL. So limit s tending to 0, f of a minus h, limit s tending to 0, f of 0 minus h, so limit s tending to 0, f of minus h, limit s tending to 0, f of minus h is minus h times sine of minus 1 by h. So this is an odd function. So this is limit s tending to 0 minus h minus sine 1 by h because sine f of x, sine x is odd function, right? So sine of minus x is minus sine x. So these two will get positive. So we will have this to be limit s tending to 0 h into sine 1 by h. Now when I apply the limit, you can see this will tend to 0 multiplied by this limit oscillates between minus 1 and 1, right? Oscillates between an open interval minus 1 and 1. So this is 0. So 0 into a quantity, 0 into a quantity that oscillates between minus 1 and 1. That means the resulting value will be 0. Yes or no? See, 0 into a number that oscillates between minus 1 and 1. So LHL is 0. Now we'll find RHL. Limit s tending to 0, f of a plus h. Limit s tending to 0, f of 0 plus h. So limit s tending to 0, f of h. So limit s tending to 0, f of h is h into sine 1 by h. Again same story. 0 into a quantity that oscillates between minus 1 and 1. Okay, it is 0. Now what is function value at the 0? It is 0. So we see that LHL is equal to RHL is equal to function value all are equal to 0. Therefore, it is continuous. It is continuous at x is equal to 0. You always note that if I have a function f of x is equal to x power m sine 1 by x when x is not equal to 0, x is 0, this will be continuous if the value of m is strictly greater than 0. Because if m is equal to 0 means what will happen? What will happen? M is equal to this become 1. M is equal to 0 means this will become 1. So this will become 1, right? So we'll have only sine 1 by x, and for that we know that it will limit does not exist, right? Okay. And m greater than 0. You can see if I multiply x with this, you can see become continuous, right? You can see at x is equal to 0, it LHL, RHL both are approaching 0. You can see here. At 0, your LHL is approaching 0, RHL is approaching 0. See how beautiful the graph is. Okay. So x into sine 1 by x, and similarly x square sine 1 by x, right? Again, you can see that it is continuous at 0. What happens when x is equal to minus 1? Again, you can see that it will have a. So what we'll do is we will just redefine this. So we will put m greater than 0, and then just a minute. What happens when x is 1 by 2? You can see at x is equal to 1 by 2, again there is some problem. So what we'll do is we'll just redefine this. We will say that this m greater than 0, and we will also redefine this m belongs to natural number, right? M greater than 0 and m belongs to natural number. Then only this will work, right? And m belongs to natural number. Okay. So we'll move on to problem number 6. The voice is clear, right? Voice is clear, right? We'll move on to problem number 6. Let f is a function be R to R be such that f of x is defined as f of x is defined as sine of a plus 1 into x plus sine x whole divided by x when x is less than 0. It is c when x is equal to 0, and this is root of x plus bx square minus root x divided by b into x power 3 by 2 when x is greater than 0. Determine the value of a, b, c so that your f of x is continuous at x is equal to 0. See, there are some unknowns here, right? A is here unknown, again the c is unknown, b is unknown. So it is given that the function is continuous at 0, right? So they are given that it is continuous at x is equal to 0. So that means limit x tending to a, f of x is equal to f of a. So since it is continuous at 0, limit x tending to 0, f of x is equal to f of 0. Since limit will also exist and equal to f of 0, that means your LHL, your RHL both exist and both are equal to also. So first what we'll do is we will find LHL. So LHC for LHL it's just enough to find 0 left hand side, right? So 0 left hand side, what is your function? So you don't need to apply that f of a minus h, both are same only. So 0 left hand side, what is your function? 0 left hand side, the function is sine of a plus 1 into x plus sine x whole divided by x. So you need to find limit for this function. You will get the LHL, left hand limit, right? So 0 left hand side, what is your limit? This is 0, right hand side, this is your limit. This is your function value at 0. You just find LHL, you just find RHL. For LHL, I'm just doing directly that I'm just finding a left hand limit. I'm just finding limit for this function at 0. That will be the LHL. You just find the limit for the function at 0. That will be your RHL. And f of 0 is C. And your f of 0 is C. Okay. Can we find limit for this function? Here you can see I cannot able to apply standard formula for this, right? Because your f of x is a plus 1 into x. When x is 0, this will tend to, I think you can apply standard formula, right? Yes. I can apply standard formula for both, right? Sine f of x. Sine f of x. So we know that limit x tending to a, sine f of x by f of x is equal to 1, provided what? F of x tends to 0 as x tends to a. So what I'm going to do is, here I have limit x tending to 0 minus sine of a plus 1 into x. So your f of x is a plus 1 into x. Let us multiply and divide by a plus 1 into x, a plus 1 into x, and here I have sine x. Yeah, I hope everyone watched the limits video of mine, which is calculus 1 and 2. Let us multiply and divide by x whole divided by x. This will be 1, this will be 1, right? Because you have to code this with the help of this. This will be 1, this will be 1. So you have limit x tending to 0 minus a plus 1 into x plus x by x. So x will get cancelled if you take common. So a plus 1 is your left hand limit. Now similarly what we'll do is we will find right hand limit. So right hand limit is limit x tending to 0 plus of, what is your right hand limit? Right hand function x plus bx square minus root x divided by b into x power 3 by 2. So whenever you see this, you just have to rationalize this. Let us multiply and divide by root of x plus bx square plus root x divided by root of x plus bx square plus root x. So numerator a plus b, a minus b. So it will be a plus b, a minus b. So a square minus b square divided by b into x power 3 by 2. See, I'm going to give you a very important thing. When you apply the limit here, this will be a finite non-zero number, right? What happens when I apply the limit here? No, it's not finite number. No, no. Actually, the thing is, suppose if I apply the limit here, suppose if this is a finite non-zero number, and if I apply limit here, what you will have? 0 plus 0 plus 0. Here I cannot do anything. Suppose if this number turns out to be some finite non-zero number, you can take that number outside, you can cancel this function. Very, very important idea I'm saying. Suppose if I apply limit here, whenever you are rationalizing this, in the denominator you will have function, right? You just see apply the limit here for this function. Here it is 0, so I cannot do anything. Suppose the number is 2, you just take 1 by 2 outside because since it's the denominator. Right? Okay, but here I cannot do anything. Let us keep this as it is. What I'll do is, let us take root x outside. So if I take root x outside, what you will have? This will be root of, if I take root x outside, it will be 1 plus bx plus 1. Yes or no? If I take x outside here, 1 plus bx. Yes, if I take root x outside, this will have. So x will get cancelled. So you will have, limit x tending to 0 plus b into x square whole divided by b into x power 3 by 2 x power 1 by 2. This is root of 1 plus bx plus 1. Okay, these two will get cancelled, right? Because x power 3 by 2 x power 1 by 2 is x power 4 by 2. So x power 4 by 2 is x power 2. Again this bb will get cancelled. When you apply the limit, what you will have? Uh, when you apply the limit, you will have what? Limit x tending to 0 plus 1 divided by root of 1 plus dx plus 1. So when you apply the limit, it will be equal to 1 by 2, right? Because this is 0, so 1 plus 1. So your RHL is 1 by 2. Now what is function value at 2? Sorry, function value at 0, function 0 at C, right? So since f is continuous at x is equal to 0, your LHL, RHL function value at 0 are equal. So what is your LHL? LHL is a plus 1. What is your RHL? It is 1 by 2. And what is your and also just a minute. I'm cancelling B here. I'm assuming that B is not equal to 0. With B not equal to 0. Because I cannot cancel 0 and 0, right? Right? I'm assuming that B not equal to 0. Okay. And what is your f of 0? It is equal to C. So that's it. So a plus 1 is equal to 1 by 2. That means a is equal to 1 by 2 minus 1. The value of a is equal to minus 1 by 2. And also c is equal to 1 by 2. See, this limit does not depends on b. But here there is a condition for b. So b can take any real number. B can take any real number except 0. Right? So that's it. Okay, okay, sorry. Actually, it is a plus 2 here, right? So a plus 1 plus 1. It is a plus 2 here, right? If I take x outside, if I take x outside, it will have a plus 1 plus 1. So a plus 2 is a plus 2. So a is equal to minus 3 by 2. C is equal to 1 by 2. B can take any real number except 0. These are the values of a and b, so that your function is continuous at that point. Okay. So you just recall definition of differentiability also, right? So when f is differentiable at a point, L of f dash of a is equal to R of f dash of a, right? On to problem number 7. Check whether f of x is differentiable at x is equal to 0, where f of x is x square sine 1 by x when x is not equal to 0, 0 when x is equal to 0. See, we need to check the differentiability, not continuity, right? Okay. F is differentiable. F is differentiable at x is equal to a if L of f dash of a is equal to R of f dash of a. So first what we'll do is we'll find L of f dash of a. What is L of f dash of a? Same idea only. What is L of f dash of a? Limit s tending to 0, f of a minus h minus f of a whole divided by minus h. This formula we have derived how it comes, right? So limit s tending to 0, f of a minus h minus f of a by minus h. So we need to check the continuity at 0. So that means L of f dash of 0 is equal to limit s tending to 0, f of minus h minus f of 0 whole divided by minus h. So what is f of minus h? What is f of minus h? Limit s tending to 0, f of minus h is h square, h square, this is minus h whole square sine of minus 1 by h minus f of 0 is 0 divided by minus h. Limit s tending to 0, h square, okay, I'll take this minus outside, sine 1 by h divided by minus h. So minus minus will get cancelled, 1h will get cancelled. So this limit is limit s tending to 0, h into sine 1 by h. This is 0, right? Just now we have seen. So your left hand derivative at 0 is 0. Now we will find r of f dash of 0. R of f dash of 0. What is r of f dash of a? Limit s tending to 0, f of a plus h minus f of a divided by h. So limit s tending to 0, f of 0 plus h minus f of 0 by h. This is your r of f dash of 0. So limit s tending to 0, f of h minus f of 0 divided by h. So limit s tending to 0, what is your f of h? F of h is h square sine 1 by h. F of 0 is 0 they have given divided by h. So again this is limit s tending to 0, h into sine 1 by h. Again it is 0, right? So you have to write like 0 into a quantity that oscillates between minus 1 and 1. A quantity that oscillates between open interval minus 1 and 1. So it is 0. So we see that L of f dash of 0 is equal to R of f dash of 0. That means f is differentiable at x is equal to 0. Very simple. Continuity means limiting value has to be equal to function value. Differentiable at that point means L of f dash of a has to be equal to R of f dash of a. We'll move on to problem number 8. Show that f of x is given as x into sine 1 by x when x is not equal to 0, x 0 when x is 0 is continuous at x is equal to 0, but it is not differentiable at x is equal to 0. We need to show that this function is continuous at 0, but it is not differentiable. Already we have shown that this function is continuous at 0, right? I'm not going to redo that. You can see that discuss the continuity of the function f of x equal to x into sine 1 by x. Already we said that it is continuous at 0, right? We already said that it is continuous at 0, right? What is that problem? Problem number 3. Sorry, problem number 6. Yes, problem number 5. Yes, problem number 6. Actually, this is problem number 7. This is 7, 8, 9. From problem 6, we already proved that the function f of x is x into sine 1 by x when x is not equal to 0, 0 when x is equal to 0, is continuous at 0. That we already proved. Now we'll say that it is not differentiable at 0. Now we will find L of f dash of A. So what is L of f dash of A? Limit s tending to 0, f of A minus h minus f of A by minus h. So we will find L of f dash of 0, because at 0 only we need to say it is not differentiable. So limit s tending to 0, f of minus h minus f of 0 by minus h. So limit s tending to 0, what is f of minus h? Minus h into sine of minus 1 by h minus f of 0 by minus h. So these two will get cancelled. You can see that you will have limit s tending to 0 minus sine 1 by h, and you can see this oscillates between minus 1 and 1, oscillates between minus 1 and 1. So that means your L of f dash of 0 does not exist. One L of f dash of 0, R of f dash of 0, both exist, both has to be finite and both has to be equal. Then only it is differentiable. But here itself we can see that L of f dash of 0 does not exist. So I can conclude that it is not differentiable at 0. But for the sake, we'll do R of f dash of 0 also. Okay. So what is R of f dash of 0? Limit s tending to 0, f of h minus f of 0 divided by h. Limit s tending to 0, f of h. So f of h is h into sine 1 by h whole divided by h. Again you can see it oscillates between minus 1 and 1. So we see that L of f dash of 0 and R of f dash of 0 does not exist. This implies f of x is not differentiable, at x is equal to 0. One next problem. So I'll give you many exercise problem in your Telegram group, right? Many similar problems are like, I don't want to do all the problems. There are many similar problems where you have to find L of f dash of a, R of f dash of a. You have to say it is not equal or it is equal. If it is equal, it is differentiable. Not equal, not differentiable. I don't want to do all the problems. So the Telegram group, I will send you problems based on differentiability, right? But this is idea. You can do anything if you know how to evaluate limits. I'll just do some unique problems so that you will not have any confusion when you are doing problem. Other than that, you can do any problem. Okay. Problem number 10. So that the function f of x is equal to mod x plus mod x minus 1 is continuous but not differentiable at x is equal to 0 and x is equal to 1. So we need to show that this function is continuous but not differentiable at 0 and 1, right? Okay. See, first you have to redefine this function. How to redefine the function is very simple. You have a function f of x is equal to mod x plus mod x minus 1. What is the 0 for this? It is 0. What is the zeros for this? It is 1. You just see for what x this will be 0. You just see what x is 0. Now you have to redefine the function as f of x is equal to, when x is less than 0, you have to redefine one function. When x belongs to 0 to 1, you have to redefine one function, right? So with less than 0, 0 to 1, greater than 0, you have to redefine one. Greater than 1, you have to redefine one function, right? Very simple. How to redefine the function? You just find the 0 for this, you just find the zeros. Zeros means roots. So inside linear, so the roots are 0 and 1. Now, you know the definition of mod x, right? What is the definition of mod x? It is plus x if x is greater than or equal to 0, minus x if x is less than 0. Now, if x is less than 0, what about the inside? See, if inside is negative, output is minus x. If inside is positive, output is plus x. Right? Okay. When x is less than 0, let us take x is equal to minus 2. Inside will be negative or positive, it is negative. So mod x will be minus x. X is less than 0. What about x minus 1? It will be positive or negative. Let us take x to be minus 1. So minus 1, minus 1, minus 2. Inside is negative. If inside is negative, output is minus of x minus 1. This is clear. When x is less than 0, you just have to see whether the inside function is positive or negative. The inside function is positive, it is plus x. If the inside function is negative, output is minus x. Right? So 0 to 1. Let us take 0.5. Modulus of 0.5. Inside function is positive, so it is plus x. 0.5 minus 1, it is negative, so output is minus x minus. See, if the inside function is positive, output is plus x minus 1. The inside function is negative, output is minus of x minus 1. Whatever x you take in this interval, your inside function is negative, inside number is negative, output is minus of x minus 1. When x is greater than 1, inside function is positive, so it is plus x. If x is greater than 1, let us take 2. 2 minus 1 is positive, so it is plus x minus 1. Right? So I have redefined the function as minus x minus x. So it is minus 2x plus 1. When x is less than 0, x will get cancelled. It is plus 1 when your x lies between 0 to 1. This is 2x minus 1 if x is greater than 1. Now you can easily check the continuity and differentiability of this function, right? At 0, you check the continuity. At 1, you check the continuity. You show that it is continuous at 0, but it's not differentiable at 1. I'll do, okay, let us do the both the thing. Continuity at x is equal to 0. First, you find LHL. So limit s tending to 0, f of a minus h, limit s tending to 0, f of 0 minus h, limit s tending to 0, f of minus h. See 0 left hand side, what is your function? Minus 2x plus 1. So your f of x is minus 2x plus 1, because I'm finding LHL. In that you have to put x is equal to minus h. This will be minus 2 times minus h plus 1. This will be equal to 1. Now you find RHL, limit s tending to 0, f of a plus h. So 0 plus h is constant function. So it is always 1. Now what is f of 0? F of 0 is here, which is again 1. We see that f of x is continuous at x is equal to 0, because LHL, RHL, f of 0 all are equal to 0. Now we'll check the differentiability. We'll check the differentiability at x is equal to 0. So first you find L of f dash of 0. So limit s tending to 0, f of a minus h minus f of a by minus h. So limit s tending to 0 f of minus h minus f of 0 divided by minus h. Limit s tending to 0. What is f of minus h? Your left hand, your f of x is what? F of minus h. So left hand side function, it is minus 2x plus 1. So replace x by minus h. Already we have did same kind of problem. This is your f of minus h. What is f of 0? F of 0 is 1 divided by minus h. This limit s tending to 0. This will be 2h plus 1 minus 1 by minus h. This will be minus 2, right? This will be minus 2. Now you find r of f dash of 0. R of f dash of 0, limit s tending to 0, f of 0 plus h minus f of 0 by h. So this is limit s tending to 0, 0 plus h. What is your f of x? 0 plus, so f of this is constant function. F of 0 is 1 divided by h. So this will be 0. Now you see that L of f dash of 0 is not equal to R of f dash of 0. That means it is not differentiable. It is not differentiable at x is equal to 0. Similarly, at x is equal to 1 also, you can say that it is continuous but not differentiable, right? You check, you do for x is equal to 1, right? I'll give you one exercise problem based on this. F of x is equal to modulus of x minus 2 plus modulus of x plus modulus of x plus 2. So that, so that f of x is not differentiable at x is equal to minus 2, 0 and plus 2. See, first what we'll do is we'll redefine the function. So f of x is modulus of x minus 2 plus modulus of x plus modulus of x plus 2, right? So what are the zeros for this? Minus 2, 0 plus 2 is a 0 for this, right? This is minus 2, sorry, this is minus 2, this is 0 and plus 2. So we'll redefine the function as x less than minus 2, x less than minus 2, minus 2 to 0, 0 to 0 to 2, and then greater than. Now when x is less than minus 2, let us take minus 3. Minus 3 minus 2 minus 5, inside is negative, so it is minus of x minus 2, and again here also inside is negative, so it is minus x. Minus 3 plus 2 minus 1, so again it is negative, so it is minus of x plus 2. Okay, now minus 2 to 0, let us take minus 1. Minus 1 minus 2 minus 3, so inside is negative, minus of x minus 2, again inside is negative, minus 1 plus 2 positive, so it is plus x plus 2. 0 to 2, let us take 1 minus 2 negative, so minus of x minus 2, 1 positive, so it is plus x. See, I'm just taking some arbitrary value inside this. I'm just seeing whether inside is positive or negative. If inside is positive, it is plus, inside is negative, minus of something. 1 plus. Greater than 2, let us take 3. 3 minus 2, 1 positive, so it is x minus 2. This is again x positive, x plus 2. So I can redefine the function to be as, I can redefine the function to be as, so minus x minus x minus x. So it is minus 3x to minus 2. So 2 minus 2 is that function. It is minus 3x, right? Because this minus plus 2 or minus 2 will get cancelled when x less than minus 2. And minus x minus 2x minus 2x plus x is minus x. 2 plus 2. So this will be 4. This is x plus 4 when x lies between minus 1 and 0. Minus x plus x plus x. So 2x minus x is plus x. 2 plus 2 is 4. So it is plus x plus 4. When your x lies between 0 to 2, x plus x is 3x, and this will get cancelled. So this is 3x when x is greater than 2. So now you can redo this, right? You can see that, yeah, I'll tell you one shortcut, right? I'll tell you one shortcut. You can also find derivative by, suppose if I want to find L of, suppose if I want to find L of f dash of 2, R of f dash of 2, you have to apply definition. I'll tell you one shortcut. 2 left hand side, what is your function? It is minus 3x. What is derivative of minus 3x? It is minus 3. That will be your answer. 2 right hand side, function is minus x plus 4. What is derivative of minus x plus 4? It is minus 1. You can see they are not equal, right? And similarly, L of f dash of, sorry, this is minus 2. Similarly, L of f dash of 2, R of f dash of 2. 2 left hand side, your function is x plus 4. X plus 4 derivative is 1. Right hand derivative, 2 right hand function is 3x. That derivative is 3. So again they are not equal. And similarly, L of f dash of 0, R of f dash of 0. 2 left hand side, your function is minus x plus 4. Derivative is minus 1. 2 right hand side, your function is x plus 4. Derivative is 1. This is what you will get the answer when you do calculations. Right? I'll tell you one shortcut. It's a very good shortcut. You just find left hand, you just see the left hand side function at minus 2, differentiate that. You just see right hand side function of minus 2, differentiate that. That will be your answer for L of f dash of minus 2 and R of f dash. Here also same only. 0 left hand side function is minus 2x plus 1. What is derivative? Minus 2. That is what you have got here, minus 2. And R of f dash of 0. So 0 right hand side function is 1. If we differentiate 1, it will be 0. That is what you got as 0. Right? Okay. You can check whether you did correct or not using the shortcut. So for our last problem, we are going to do today, problem number 12. X square plus 3x plus a, if x is less than or equal to 1, bx plus 2, if x is greater than 1, is differentiable at x is equal to 1. Find the value of a and b. So we need to find unknowns, right? We have solved this kind of problem in limits. So they will limiting value is given. We need to find unknowns that we did by Maclaurin series, right? Okay. So whenever they are saying that it is differentiable at 1, we need to find unknowns, right? Okay. Okay. Start with, since it is since it is since it is differentiable at x is equal to 1, it is also continuous at x is equal to 1, right? So that means your limit extending to 1 f of x is equal to f of 1. This will be true. So first what we'll do is we will find LHL at 1. So limit s tending to 0 f of 1 minus h. So limit s tending to 0 f of 1 minus h. So f of x is x square plus 3x plus a. That is 1 minus h whole square 3 into 1 minus h plus a, right? F of 1 minus h, this is your function f of x. So this is limit s tending to 0 1 plus h square minus 2h plus 3 minus 3h plus a. So when h is 0, you will have 4 plus a, right? So 4 plus a is your LHL. Now we will find RHL. RHL is limit s tending to 0 f of 1 plus h. So limit s tending to 0 b into 1 plus h plus 2. See, these kinds of problems that you're already familiar, right? I'm just doing directly. So when I put 0, you will have b plus 2. So b plus 2 is your RHL. Now what is f of 1? So f of 1 is here, right? F of 1 is also b plus 2. Now since f is continuous at x is equal to 1, your LHL, your RHL, your function value all to be equal. Your LHL is 4 plus a, your RHL is b plus 2, function value is b plus 2 again. That means these two has to be equal. So 4 plus a is equal to b plus 2. So that means a minus b plus 2 equal to 0. Call this as equation number 1. Now it is also differentiable, right? It is also differentiable at x is equal to 1. So find L of f dash of a. So what is L of f dash of a? Limit s tending to 0 f of a minus h minus f of a by minus h. We'll check L of f dash of 1. So L of f dash of 1 is equal to R of f dash of 1. So limit s tending to 0. Can we do shortcut? Can we do shortcut? You can use definition also, or you can use shortcut also. What is your left hand side function of 1? Left hand side function is x square plus 3x plus a. What is your derivative? 3x, 2x plus 3 plus a. Apply the limit 1, you will get the answer. But I'll go with definition. So f of 1 minus h minus f of 1 divided by minus h. After differentiating, you need to apply the limit also. So limit s tending to 0, f of 1 minus h. So 1 minus h is 1 minus h whole square 3 into 1 minus h plus a minus f of 1. What is f of 1? 1 4 plus a divided by minus h. So limit s tending to 0 1 plus h square minus 2h plus 3 minus 3h plus a minus 4 minus a whole divided by minus h. Right? So what you will have? A will get cancelled. Minus 4 plus 4 will get cancelled. You will have limit s tending to 0 h square minus 5h by minus h, right? H square minus 5h by minus h. Okay. So if I take h common, you will have h minus 5 by minus h. When I apply the limit, you will have 5. You can also check whether you did correct or not. What is your L of f dash of 1? It turns out to be 5. Suppose if you want to find L of f dash of 1, you just differentiate this, right? If you differentiate this, what do you will have? Left hand side, it is 2x plus 3 plus 0. You just put x is equal to 1, you will have 5, that's it. Because at 1 you are finding no. Just differentiate left hand side function. And similarly, what will be your right hand derivative? You just differentiate this. It is b. So you'll have only b. Now r of f dash of 1. So r of f dash of 1. See, from this result we can clearly see you differentiate this function, you will have b plus 2. Sorry, yes, b. When you apply the limit, if there is no, it is independent of x, it is constant. So it will be b again, r of f dash of 1. But we will do by definition, f of 1 plus h minus f of 1 divided by h. So limit s tending to 0, f of 1 plus h. So b into 1 plus h plus 2 minus what is f of 1? 4 plus a, 1 plus 3 plus a. So again this 4 plus a divided by h. So limit s tending to 0, b plus bh plus 2 minus 4 minus a divided by h. So this will be limit s tending to 0, bh plus b minus a plus 2 divided by h. A minus b plus 2. Is there any mistake I am making? F of 1 is b plus 2. No, f of 1 is here only, right? 4 plus a only. Function is here only, it is f of 1. F of 1 plus h, b into 1 plus b 4 minus a by, sorry, this is minus 2. So b minus a minus 2. Okay. So this is limit s tending to 0. If I take minus outside here, you will have a minus b plus 2, right? A minus b plus 2 divided by h. We know this term is equal to 0, right? We know this term is equal to 0 from 1. From 1 we have a minus b plus 2 is equal to 0. So that means we will have limit s tending to 0, bh by h is equal to b by definition. But you can directly differentiate this. So it is differentiate is bx plus 2 b. Okay. So since it is differentiable at x is equal to 1, L of f dash of 1 is equal to R of f dash of 1. So L of f dash of 1 is 5, R of f dash of 1 is b. So we have got b to be equal to 5. And from 1 we know that a minus b plus 2 is 0. So that means a minus 5 plus 2 is 0. That means a is equal to 3. So that when a is 3 and b is equal to 5, the function will be continuous as well as it is differentiable also. Right, okay. So in the telegram group I'll send you some problems based on continuity and differentiability. You just practice this problem. I'm going to wind up this topic, continuity and differentiability. Very simple. They will give one function. At some point they will ask you whether it is continuous or not. Just apply definition and get the answer, right? So that's it. So in the next class we will continue from the next topic. In telegram group I'll send you notes, right? If you haven't joined telegram group, I'll the description there is a telegram group link, you can join them. Okay, thank you. Good night. Bye.